ladies and gentlemen, our focus today is going to be on actually making those Lewis dot structures for compounds. If you remember from our last video, our focus was just making on the elements with the dots that represent the number of valence electrons that surround the atom. Well, today we're going to go through the little bit more of a complex process in actually building the structures of chemical compounds utilizing Lewis dot structures. Now, these are very important. These help us understand how chemicals bond with one another, how many times they covalently bond, and what their structure is. So this provides us with a lot of information moving forward about the particular compound or molecule that we're looking at today. So just one primary learning target for today. Hopefully you will be able to draw Lewis structures for a variety of compounds. And in case you're listening, the key word for this video is variety. So make sure you write that down in your video notes. We have a couple of key vocabulary terms here for you to make sure that you understand. The first one being single bond. We'll also talk about double bond, triple bonds, and resonance structures. So a little bit about Lewis structures. Keep in mind that compounds themselves, not just single elements, can be represented by a Lewis structure. A Lewis structure helps us understand how many single electrons are located on the outside of an atom, as well as how many electrons are involved in the chemical bonding of the elements to make up the actual compound. So when we draw these out, we use dots to represent the lone valence electrons. We use single lines to represent the fact that two elements are sharing a pair of electrons, thus creating a covalent bond. So here you see nitrogen has one pair or two electrons. We call those a lone pair because they're by themselves. I'll let you insert your own normal Mr. Lamb joke here about being alone. And then if you look, there's a line between nitrogen and chlorine, and there's 1, 2, 3 lines between 3 different chlorine atoms. Those represent a pair of electrons that are shared between nitrogen and chlorine. So you can see here, there's a variety of different ways we can represent electrons in a Lewis dot structure. Now keep in mind that multiple electron pairs can be shared to form double and triple bonds. So in some cases, you're going to need to check to see if you have the correct number of electrons in the structure and so on. If not, you're going to need to add double and sometimes even triple bonds in order to make the Lewis structure work. You'll see what I mean when we go through and do some practice problems. One other thing to keep in mind is that when we are drawing structures, it is imperative to keep the correct number of electrons while satisfying the octet rule. Remember that they can only have a maximum of 8 electrons in their outer shell. In fact, that's what they want to have in order to be most stable. Also keep in mind that hydrogen follows a duet rule because there's only an s orbital in the first energy level. They can only have a maximum of 2 valence electrons. So if we look here at the structure, everything's bonded correctly, but if I look at, let's look at the chlorine on the left here. We have 2, 4, 6 valence electrons that are not bonded, and they also have 2 electrons in that chemical bond that share between chlorine and nitrogen. Therefore, they have 8. Remember that line, those electrons are shared between chlorine and nitrogen, so you kind of count them for both. The nitrogen has a pair of electrons that are by themselves, a lone pair of electrons, and 1, 2, 3 chemical bonds. Well, remember there are 2 electrons in each of those chemical bonds, so there's 6 electrons there. I look at the chlorine underneath. Again, you see 3 lone pairs for 6 electrons and a bonded pair for 2. And then on the right hand side, again, you see 6 lone pairs and a bonded pair for 2. 2 plus 6 is 8. So the octet rule is satisfied for all of these different elements. Now 9 times out of 10 that will happen. There are a few exceptions to the octet rule, those of which we will talk about in class later on. Alright, so there's a lot that's really going on here. There's actually 6 key steps to drawing Lewis dot structures. It's really important that you understand and know all of these 6 rules and follow them each and every time. So step 1 is determine the type and number of atoms in the formula. So we need to know what atoms are in the formula, and that's going to help us decide what type of structure we're going to build. Step 2 is determine the total number of valence electrons, so you can find that information on your periodic table. Step 3 is determine the central atom. Now, you need to look at all of the atoms that are available in your molecule. The one that is the central atom is the one that is going to be the lowest electronegativity. That is the one that is furthest away from fluorine. The only exception to this is to not use hydrogen. Okay? Hydrogen will not be a central atom because it can only have 2 electrons in its outermost shell. So it doesn't really bond to a whole lot of other things. Step 4 is to bond your other atoms to your central atom with single bonds. And then step 5 is to add pairs of valence electrons to all atoms to reach the octet or duet rule. So in step 6, you need to count the number of electrons in your structure. And if it's equal to the total number of valence electrons you calculated in step 2, you are done. If not, you need to remove 2 lone pairs of electrons and create multiple bonds until the number of electrons in the structure and valence electrons is the same. What that means is that if you have more electrons in your structure than the number of valence electrons, you need to pull out 2 lone pairs of valence electrons between 2 atoms and then add a double bond. Okay, you'll see what that looks like here in just a minute, but that reduces the number of electrons, yet still satisfies the octet rule. And you continue to do this where you can double bond until you find that the number of electrons in the structure and valence electrons is the same. Let's look at some practice problems and put this in action. Alright, so it's asking us to draw out the Lewis structure for CH4 and HCN. So we need to take a look here. So we got CH4 and HCN. Let's do CH4 first. Okay, so the first step, let's count up the total number of valence electrons we have to play with here. So we got a carbon and 4 hydrogens. Carbon, when I look at my periodic table, has 4 valence electrons. Hydrogen, each one has 1, but since there are 4 of them, I have 4, so that makes 8. Off to a good start. Next step, determine your central atom. We have carbon and hydrogen. If you remember what I told you, hydrogen will never be the central atom, so our choice is carbon. So we're going to draw that here. Now, the next step is to attach every other element with single bonds. So, hydrogen here, hydrogen there, hydrogen there, and hydrogen there. The next step is to make sure we satisfied all of the octet and duet rules. So we take a look at each element in the compound. This hydrogen here has a single bond attached to it, and that accounts for 2 valence electrons, so its duet rule is satisfied. Same for this hydrogen, and this one, and this one. I take a look at my carbon. My carbon has 2, 4, 6, 8 electrons attached to it, which are represented by 4 single bonds. So we're going to remember those single bonds are shared between the 2 atoms that they come in between. So I take a look there, all of my octet and duet rules are satisfied. So we're good. The next step, count up the total number of valence electrons we used in our structure, and if it equals the number of valence electrons we calculated in step 2, we are done. So if I take a look here, we've got 2, 4, 6, and 8. So I have a total of 8 electrons in my structure. I need 8 electrons, so I am done. And that is the Lewis structure for CH4, or methane. I'm going to take away these dots here. Take away those dots there. I didn't want you to think there was rogue electrons just roaming around. Okay, so that is the Lewis structure for CH4. Let's move on to the next one, an HCN. Let's follow the same rules. Okay, so HCN here, we need to see we got a C, an H, and an N. Carbon has 4 valence electrons. Hydrogen has 1. Nitrogen has 5. Again, you can find those in the periodic table. So the total number of electrons in our structure we need is 10. So our next step here, determine our central atom. We have hydrogen, carbon, and nitrogen. Remember, hydrogen can never be the central atom, so we're going to use either nitrogen or carbon, and you'll find that the one that's furthest away from fluorine, the one with the lowest electronegativity, is carbon. So we'll draw that. We're then going to attach everything to carbon with a single bond. Now we need to satisfy the octet rule, or duet rule. So hydrogen has a single bond attached to it. That counts for 2, so we're good there. Carbon has 2 single bonds attached to it. That counts for 4. So we need to add 4 electrons. There's some wonky looking electrons, aren't they? Nitrogen here only has 2. It needs to have 8. So we're going to 1, 2, 3, 4, 5, 6. So now it has 8 in its outer shell. So I take a look. I'm going to count up the total number of electrons I put in my structure. If it equals 10, we're done. So we got 2, 4, 6, 8, 10, 12, 14. So I have a total of 14 electrons in my structure. So that's not going to work. So the rule is to remove 2 lone pairs of electrons. So let's remove the 2 top pairs here, like that. And then I'm going to add another bond in between where I got rid of the lone pairs. So now we have a double bond between carbon and nitrogen. What's nice about this strategy is that everything still satisfies the octet rule. If you look at carbon, carbon still has 3 single bonds attached to it and a lone pair. That's a total for 8. Nitrogen has 2 single bonds attached to it and 2 lone pairs for a total of 8. So let's count them up again. So we got 2, 4, 6, 8, 10, 12. Well, we're now down to 12 valence electrons. So we're going to follow the same rules. We're going to eliminate 2 lone pairs of electrons, and we're going to add another bond between carbon and nitrogen. Again, notice that all the octet rules are still satisfied, so let's take a look. We've got 2 electrons here, 4, 6, 8, 10. So we're good. We're supposed to have 10 valence electrons, and our structure has 10. So we're done. Okay? So it takes some time to understand completely and be able to work through that process, but take it one step at a time. Always follow those rules, and you'll find that this is pretty easy and pretty straightforward to do. Let's do a couple more practice problems. So we've got 2 more Lewis structures to draw here. CH2O and NO3 with a minus sign next to it. We'll talk about what that means here in just a moment. So let's start with CH2O. So we're going to start C, 2 hydrogens, and an O. So we got 4 here, 2 here, and 6 here, for a total of 12 valence electrons in our structure. Again, we're going to take a look at which one will be our central atom. It's either carbon, hydrogen, or oxygen. Again, hydrogens don't count. So carbon and oxygen, the one furthest away from that will be carbon. Attach everything to your central atom with single bonds. Draw lone pairs to satisfy the octet rules. Well, hydrogen has a single bond attached to it. That's 2 valence electrons, so we're good there. We're good with the other hydrogen. The oxygen needs 1, 2, 3, 4, 5, 6. And carbon's going to need 2 because it has 3 single bonds attached to it, which make up 6 valence electrons. So let's count them up and see if we get 12. 2, 4, 6, 8, 10, 12, 14. So we have 14 valence electrons here. So we need to take away 2 lone pairs and add a double bond in between where we take away the lone pairs from. So the only place we can take away lone pairs is from the carbon underneath and the oxygen up top. And then we're going to add another bond in between them. So let's take a look now and see if we get 12. So we've got 2, 4, 6, 8, 10, and 12. So we've got 12. We wanted to get 12. We're good. This structure checks out. Awesome. Let's move on to the next one, which is NO3 2. And so we got NO3 with a -1. Now, that minus tells you something. If you remember that we talked about this before, your charges on there indicate how many either extra electrons or fewer electrons you have. So since there is a minus, we are going to add 1 electron to our structure. Okay? So N is 5. Each oxygen is 6. Remember, you find that on the periodic table for a total of 18. We're going to add 1 more to that. So our total is going to be 24. All right? So let's go ahead and start building our structure. Nitrogen and oxygen are our choices between our central atom. So nitrogen is the bad boy here. We're going to add lone pairs to satisfy the octet rule. So 2, 4, 6, and then 8's there. 2 on my nitrogen. All right. So let's count them up and see if we get 24 valence electrons. So you got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have 26 electrons in our structure. So we need to take away 2 pairs and then draw a double bond between them. Now, in this instance, you can really draw that double bond anywhere between the nitrogen and the oxygen. Okay? So what I'm going to do is I'm just going to take away 2 of them from this oxygen and the nitrogen and add a double bond. And so we count them up again. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And we're good. Okay? The key thing here is that double bond can exist between any of those pairs of atoms. Okay? You end up with essentially the same structure, but they are known as resonance structures. Okay? So realistically, you could draw it like this. where the double bond is there, or you could draw it where the double bond is there. Those are known as resonance structures. Now, I may ask you to write out all the possible resonance structures. Remember, that can only occur if you have that double bond that can essentially rotate around those atoms and doesn't necessarily change the structure of the molecule itself. The other thing we need to do is if there is a charge that is associated with it, we typically put it in brackets and we indicate that it has a -1 charge. Again, some people will tell you to do this, some people won't tell you to do this. I want you to do it. I think it helps you understand that there's a -1 there and helps you understand that it's an ion as well. All right? Let's move on to one more practice problem. Draw the Lewis structure for O3. Well, pretty straightforward here. We got O, we got 3 of them, so we're going to have 18 in our structure. All right? No central atom here because we've got, well, 3 oxygens, so essentially it's going to be oxygen, oxygen, oxygen. All right? Now, we need to add lone pairs to satisfy the octet rule. So on the ones on the outside, we're going to add 6 electrons. And the ones in the middle, we're going to add 4. All right? Pretty straightforward here. So let's count them up and see if we get 18. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18. We have 20. So again, we need to remove 2 lone pairs and draw a double bond between them. Okay? Now again, think about this. Could that double bond have been placed somewhere else? And the answer is yes. There is a possible resonance structure for this. So if we were to draw this the other way with the double bond in between the other oxygen, it would look something like this. Okay? So those are your 2 possible solutions there. Remember, this is known as a resonance structure. The more practice you get with this, the better off you're going to be, and the better you'll start to be able to see relationships between where you put the bonds and how the double and triple bonds work. We'll practice with this a lot more as we move in class. Some key tips from the Joe Lamb. Follow the rules in order. Yes, I'm being serious. Do not skip steps. I don't want you to make mistakes. All right? If you do see something with multiple carbon atoms, those carbon atoms typically form a chain. So for example, something like C3H8, which is known as propane. I'll sell propane and propane accessories. That boy ain't right. Oh! This is my worst Hank Hill impersonation ever. Point is, if you have multiple carbon atoms, they typically form chains. So put all those carbons together. Look for ion charges. Make sure you add or subtract electrons. So if it's a negative charge, you're going to add an electron. If it's positive, you subtract 1. Don't forget to follow the octet rules. And in some instances, smaller atoms and noble gases don't always follow the octet rule. Sometimes there's elements like boron trifluoride, where boron will only have 6 electrons attached to it. Or xenon hexafluoride, where it can have 12 valence electrons on it. Be aware for some of those. We'll talk about some of those exceptions in class as well. Long story short, make sure you follow the rules. There are several key steps when drawing out Lewis structures of compounds. And be sure to consider the number of valence electrons, the central atom, and satisfying the octet rules when drawing out a variety of different Lewis structures. You can always check for these. Make sure the number of electrons in your structure is the same as the number you calculated in the beginning, and make sure all of your octet rules or duet rules are satisfied, and you'll have no problems whatsoever. Hopefully you got a lot out of this video. I know it's a bit of a long one, but I think you guys will really appreciate it, really understand it, and hopefully you guys have a great day. We'll talk to you later. Bye-bye.